Hi, my name is Tiagi, and in this video, I'll be going over Unit 7, rotation, which you will need to know for the AP Physics 1 exam. So to start, the number one tip I can give you guys is whenever you're faced with a rotation problem, always think of the problem, how you would solve it, in terms of translational terms, or translational variables. So again, the number one tip is that all the translational terms we have learned before, like momentum, energy, kinematics, they all transfer over to rotation. So let me show you some examples. So in linear terms, we have force, right? And our equivalent for rotation is torque, which is given the symbol tau. In linear terms, we have mass. Rotational terms, we have moment of inertia. Or rotational inertia is another name of it, given the symbol I. With these two, and actually we also have acceleration, right? Linear acceleration, angular acceleration for rotational terms. And so with these formulas, we know that F equals ma is the formula for a linear equation, and for our equivalent for rotation is torque equals rotational inertia times angular acceleration alpha. Okay. Similarly, we have velocity, that becomes angular velocity omega, and we have delta x displacement, which becomes delta theta, or angular displacement. And of course, with these formulas, we also have the idea of kinematics formulas for rotation. So we have delta theta equals omega squared minus omega initial squared over 2a, or 2 alpha. We have delta theta equals omega t minus 1/2 angular acceleration t squared. We have delta theta equals the angular velocities averages times time. We also have that delta theta equals omega initial times t plus 1/2 angular velocity t, or angular acceleration t squared. And we have that angular velocity equals angular velocity initial plus angular acceleration times time. So those are our kinematics equations represented using rotational variables. So let me explain a little more about torque and momentum inertia. So torque is a measure of, it's the ability of a force to make an object rotate. Okay, and so the formula for torque is equal to force perpendicular times radius, or radius perpendicular times force. What does the perpendicular part mean? Well, I'll show you. Let's say we have a door handle, or a door, hinged here at a pivot, and the door extends out like this, like in a straight line. And let's say we apply a force at an angle, like so, and the force is angle here, theta. So there's two ways we can calculate torque. We can try the first way, force perpendicular times radius. So this is radius. So the force perpendicular would be a force like this, right? And we would note to this is force, this would be force sine theta, right? So the torque is equal to R F sine theta. Or we have this formula too, right? So we can also draw a line of action of the force, and we can draw the perpendicular of the radius to this line of action. So we imagine the force goes on in a straight line. That's the line of action, and then we take the perpendicular from this line of action to the pivot. And so I'll erase this. This is just F, right? If this is R, right, and this is theta, this also equals theta, and this is R sine theta by the hypotenuse is R, right angle, theta, R sine theta. So this also equals R sine theta times F, which is just the same thing as this. So there are two ways to look at torque from a diagram. And of course, if the force is acting right like here at the pivot, we know from opening a door, right? If you put the force right at the edge of the door, it's not going to rotate. And this is the reason why, is because we're adding a torque right to the pivot point, that means there is no perpendicular force. And because there's no perpendicular force, that means the perpendicular force is 0, so our total torque is 0. And because the total torque is 0, no torque is done, therefore the object doesn't rotate. Next, I'll look at the moment of inertia. So moment of inertia represents the how difficult it is for an object to rotate. Okay, so while for mass is a measure of how difficult it is for an object to change its acceleration, moment of inertia is how difficult it is for an object to rotate in the system. So while mass only depends on the weight of the object, moment of inertia depends on not only the weight of the object, but how the weight's distributed in the system relative to the point you're rotating. So on the AP exam, they're going to give you all the i's. So they ask you a question, and you need the I. They'll give you, they'll say I equals blah, blah, blah. But sometimes some helpful ones to remember is that I equals mr squared. This is for a point mass. And that's really the only one you have to remember. All the other ones they're going to give you on the exam. And another one you should know for formulas is that the sum of a system, the i's in a system, is equal to the sum of the i's, the objects, okay, all the objects in the system, their i's, is the total sum i's. Okay, next. So we did torque, we did moment of inertia. Now let's just look at these and see how can we convert them into linear. We want to convert linear to angular terms, or rotational, might be a better word. Okay, so let's imagine we have a circle, right? And the circle has a radius r, and we create a arc of angle theta, and the arc's length is x, okay? So first I'm going to use some basic rules. So I'm going to say x over 2 pi r, right? So x is here, 2 pi r is the entire circle circumference, equals theta, and we want this equal to a proportion, right? So x over the entire circle, 2 pi r, theta over the entire circle is 2 pi, so 2 pi. So if we multiply by 2 pi r, what we get is x equals theta over r. And this is one of our translations, linear to rotational. Linear x is equal to theta times r. Now you can see if we divide by t, what we get is velocity equals theta over t. You might not know what that is, but if you know that x over t is velocity, right? And these are all equal terms, right? Then theta over t must equal angular velocity. So this is equal to angular velocity times r. So tangential velocity equals angular velocity times r. Same thing, we can do that again. Divide by t, we'll get acceleration is equal to angular acceleration times r, because omega over t, again, same idea, equals acceleration because it's v over t in linear terms, and therefore it equals that in angular terms. So again, the idea here is that whenever you have a problem, you can always think about it in linear terms, and it'll help you figure out what it means in angular terms or how to solve it. And so that's our equation for linear to rotational. Okay, next, let's imagine we have a circle, or we have an object, right, that's going in a circle, or at that point of its motion, it's going in a circular motion, so it's rotating. So here, the object has a tangential velocity this way, and because it's going in a circle, right, we know this from UCM, the object has a radial acceleration going this way as well. So we know from UCM, the radial acceleration equals the velocity squared over r, and we can convert this into a easier way to understand. So omega, first of all, omega equals 2 pi over t, or period, 2 pi over period. And the reason why is, let's say we have a circle, right? And imagine that. So 2 pi over t, 2 pi is the total amount of angle in a circle, 2 pi, right? And t is the amount of time it takes to do one rotation around the circle. So dividing 2 pi divided by t, we get the velocity, or the angular velocity, it takes to go from here to here around the circle. Because again, 2 pi is the entire circle, t is the time it takes for one rotation. So we have this formula, right? So we can say that velocity is equal to 2 pi r divided by t. And again, this is just based on our formula, velocity equals omega times r. Now, if we plug this into here, what we get is 2 pi t squared over r squared divided by r. 2 pi over t is omega, right? So again, omega squared times r. So angular or radial acceleration is equal to omega squared times r, which is another useful formula to know that you can also just derive fairly easily. Okay, next. Next, let's talk about angular momentum. So the same way we have linear momentum in linear quantities, we have angular momentum. So the main formula we need to know is that the sum, actually first we'll define angular momentum. So angular momentum is equal to the radius times the perpendicular of momentum, or in other words, r times mv perpendicular, or I times omega. And this just comes again from the idea that mass, this is velocity, right? P equals mv. And we also have, based on this logic, torque times delta t, which comes from the logic that momentum is equal to impulse, j, which is equal to force times delta t. Converting those into linear terms or rotational terms, we get these equations. So momentum is equal to all of these rp, rmv, I times angular velocity, and torque times time. And the main formula with angular momentum is that the sum of the initial angular momentums, given the symbol L, is equal to the sum of the final angular momentums as long as no external torques. Okay? Same thing holds for linear, right? As long as there's no external impulses, angular momentum is conserved. Same thing with angular rotation, as long as there's no external torques, angular momentum is conserved. And last thing, we'll go over energy quickly. So for kinetic energy, we've been focusing on how kinetic energy is equal to mv squared over 2. And this is not entirely correct. This is translational kinetic energy. There's also rotational kinetic energy, which is equal to I omega squared over 2. Right? And kinetic energy as a whole is equal to k translational plus k rotational. So in all the problems we've done this year, we've sort of not done the right k, because k is equal to translational plus rotational, but we're able to not, say rotational, because in all our problems we've done this year, rotational is just 0. But now, since we're focusing on rotation, we have to factor in that the rotation also has a kinetic energy associated with it, given by this formula. And I think that should be it for formulas. I guess one more thing. So we have the formula work equals force times distance, right? So for torque, we have torque is equal to, or sorry, not torque is equal to, work in rotational terms is given torque times theta, and then power, right? Power is equal to force times velocity, and that's given work is equal to torque times angular velocity in rotational terms. Okay, great. Now let's do some practice problems with this. So first, let's imagine one with kinetic energy. Let's say we have a sphere on a cliff or on a slope. Can't really draw a sphere, but that's a sphere, and it's rotating, right? Rolling, I guess, is a better way, down a hill or down the slope of height h. Okay, and we want to find the v uh, given m, and let's say we're given r2. Although I don't think we need either, but let's say we're given m and r. Okay, So the first things first, we know based on conservation of energy that UG1 is equal to K1s, or K2. So UG1 here is equal to K2 there. UG1 is the same as always, equals MGH. Now K2 must equal, again, translational plus rotational, so mv squared over 2 plus I omega squared over 2. So I forgot to say, let's say they also give us the I is 2/5 mr squared. So on the AP test, they're going to give you all the I's, so you don't need to memorize this, but they'll give you the I. And let's say that the object is not slipping. And so this is important. If it's not slipping, we remember that velocity equals omega times r, but this is only true if the system is not slipping. In this case, it's not slipping, so we know that velocity equals omega times r. Because as we roll down the hill, our angular velocity is directly converted into linear velocity based on this formula because it's not slipping. It's angular converted to linear, like so. So now we have to plug this in. So let's say we convert this into omega equals v times r. We can plug this and this into this. What we get is we get I, so I is 2/5 m r squared times velocity squared over radius squared times 1/2. The 2's cancel out, the r's cancel out. We're left with mv squared over 5 plus mv squared over 2, which is the translational term, equals mgh, right? So the m's cancel out because they're all in each term. These two added together is 7/10 v squared equals gh. Therefore, v equals square root 10/7 gh, which is our final answer for this problem. So again, the process with kinetic energy for rotational systems, you do the same process, set conservation of energy. Then we use our formulas to expand it, and then we use the fact that the I and it's not slipping to plug into the I omega part, and then we can solve for velocity based on our equation. Next, let's imagine a rod that's on a pivot and is above the ground by a pole, like so. And so we let the object go and it rotates, you can imagine it's going to swing down like that. So the rod has the length L and a mass M, and the I of the rod is 1/3 m L squared, and we want to find angular acceleration of the rod at this point specifically. So we know that the angular acceleration equals torque. From the formula, torque equals I times A, so angular acceleration is A equals torque over I. So we need to find torque. We have the I, we need to find torque. So torque, we know, is force times radius, but where do we apply the force? So in a system like this, since it's a uniform rod, okay, we apply the force at the center of mass. So the force of gravity is applying at the center of mass, which is at L over 2, because it's a uniform rod. And the reason why we apply the force at the center of mass is because by the definition of the center of mass, all the forces we can assume are being acted on that center of mass because that's where all the mass is concentrated. So force of gravity is acting here, it's acting perpendicular, so radius is L over 2, force of gravity is equal to mg, so our torque is mg times L over 2, so mg L over 2, divided by I is ml squared over 3, so we're really multiplying by 3 over ml squared, so m's cancel out, the L goes in the bottom, and we're left with angular acceleration equals 3g over 2L, which is our final answer. So torque, really simple, same way we do forces and masses. We look at the forces, apply the forces into our second law equation, and then we just solve for whatever value they want us to solve for. And lastly, we'll do one quick momentum problem, angular momentum. I'll just explain how we do it. Let's say we have a disk rotating. It's a radius r, mass disk, md. And let's say we have a ball being thrown this way. Mass of the ball is mb, velocity is v. And we want to find out the final let's say it sticks. Okay, let's say this is the initial state, and it sticks onto this disc, and it starts rotating together as one system. And we want to find the final angular velocity of the system. So we know, based on conservation of angular momentum, that the angular momentum initial equals the angular momentum final, and this is because there are no external torques within the system. Within this system, right, there are no external torques being acted. So angular momentum initial, so the angular momentum initial, this is not moving, this is moving. And so does this have an angular momentum? And the answer is yes, because even though it's not rotating, right, it's going straight, it is rotating relative to the center, to the pivot here. Because think about it, the radius here is r, the radius as a further point is r here. So the radius is changing, therefore it is rotating, even though it's going straight. Relative to this point, it's rotating like a circle. So angular momentum initial equals rmv, which equals to angular momentum final, which is equal to, and again, rmv is the reason why it's rmv, is because we draw a line here for r. The velocity is perpendicular to r like that. Okay, so rmv equals angular momentum final, which equals the I of the ball plus I of the disc combined, because again, the I of the system is equal to the sum of the I of the objects, object 1, object 2, add this together, times omega final, because again, this is another way of writing the formula for angular momentum, and then we just say angular momentum is equal to rmv divided by IB plus ID, and that's our final answer. And of course, they're going to give us IB and ID so that we can figure out the values. And that's how we do angular momentum. So it's very similar to linear momentum. Same idea, we just do a little bit different stuff. So yeah, the idea with any of these rotational problems is once you know the equations and formulas, it really is the same as solving a linear momentum problem or linear anything problem, right? And my recommendation for you guys when you're solving these rotational problems, first think about how you would solve it in linear terms, and then once you figure out in linear terms, think about how you could translate that into rotational terms. Because all of linear quantities have a rotational equivalent, which allows you to solve them fairly easily. So if you know that your linear stuff, then rotation should really be easy because it's all just that stuff, but just different symbols. So same idea. Okay, enough talking. That's it for today. Thank you guys all for watching, and I hope to see you guys all tomorrow. Bye.